Okay, I'm connected with computer. Okay, so everybody, I have a student. What's your name again? I'm sorry.
Matt.
Matt's in my office, and he had a question, and I'm going to take a video of the answers about how to prove something with induction, in particular one of the homework problems. So we'll go over the solution, hopefully, of that problem, and hopefully this will be helpful for those that haven't seen induction or need a little brushing up on it. So I'm going to join with my iPad. Actually, I don't want to do that. Well, actually, you have to go, you can look at it.
What's that?
But if you have to go, then
I've got about an hour.
okay, that should be sufficient, hopefully. If it's not, then we're going to have to cut some problems out. Okay, let's yeah. All together. Okay, sure. All right. Okay, so here's what I'm going to do for you. Put this screen here. You can see what I'm writing. I turn video off so that you're not here. Okay. All right, so that's not what we're doing. Let me go here. Sheet here. All right, so induction. So the problem is that our NASS is, this is problem, I'm sorry, what was the number of the problem?
1.7.
1.7. And it asks for a formula of powers of the following matrix. If I remember correctly, tell me if I'm making a mistake here. So it says, consider this the nth power of this matrix and find a formula for it. So find a formula. And then, or it says prove, okay, so we'll do that. That's always an adventure. And then when we're done with that, we then can prove by induction that our formula is correct. So prove it's true, it's correct by induction. Okay, so that's the question. So the way I go about solving this is I want to first address this find the formula part, right? To do that, I start at 1 and I know exactly what it is, right? I have this matrix. So a matrix to its first power is just itself. So this is what I get. Okay, so now for n equaling 2, I have to do just a little bit of matrix multiplication. And I can do that. I guess I don't need to do that. I can do that just using some arithmetic. So let's take a look. Let's see what we get. So I'm just going to multiply first row, first column, get 1, first row, second column, I get 1 times 1 plus 1 times 1 plus 1 times 0. So I get 2 1s, I get 2. And then the third one, I get 1 times 1 plus 1 times 1 plus 1 times 1, I get 3. Now I'm going to give you guys, you Matt, a trick. I noticed something about this in a little vocab here. This matrix has a special form, namely, if I look at the diagonal entries, well, those are non-zero, but everything below the diagonal entries is 0. This is what we call an upper triangular matrix. Just see like a triangle in the upper part. It's upper triangular. When you have an upper triangular matrix, let's say you have 2 upper triangular matrices and you multiply them together, it's not hard to show that actually that will also be an upper triangular matrix. So using that fact, and if you want, you can just compute this, you can actually, I can fill in 3 of these entries right away. But now I need to make a little more computation. So if I look at the second row and the second column, and I take their sort of dot product or multiply them, I'll get 0 times 1 plus 1 times 1 plus 1 times 0. I get 1 here. And then one more time, I can calculate here to be 2, and I'll calculate here to be 1. So this is my n equaling 2 case. Not enough for a pattern yet. So I'm going to do one more and see if I can't detect a pattern. So I'll put this guy here, put this guy here. I'm taking the third power, which is the same as squaring it and then multiplying again. And let's see if we can't find a pattern. Don't be afraid to experiment, right? I mean, it's like, just keep on going until you feel like, well, I'm done. Like, I think I see a pattern. So again, these are upper triangular, so I can kind of fill out these. And you'll notice something that also for upper triangular matrices, if you look on the diagonal and they're all 1, they'll always, and you take a product of 2 matrices where the diagonal is upper triangular and on the diagonal they're all 1s. You're going to end up with all 1s on the diagonal again. So that raises the question, you know, what we're really looking for are these formulas. What's in here? So let's take a look. So if I take the first row, second column, I get 2 plus 1 plus 0. So that's 3. And then the first row, third column, I get 3 plus 2 plus 1, which is 6. All right.
There we have our pattern.
I'm sorry?
And there we have our pattern.
And you're seeing a pattern already. That's great. So here, and then I get 1, I take this one, the second row, third column. If I do that, I'll get 3 here. Okay. So you see a pattern. That's fantastic. That's good. Okay, so Matt, not to put you on the spot and to record you while you're doing it, what do you think the pattern is?
Well, I'm saying that we have multiplied what I'm noticing is instead of being 1, 2, 3, now we're jumping 1, 3, 6. And so I'm betting that if we go to the next iteration up, we're going to go 1, 6, 10. And then going from there.
Where are you seeing 10?
Speculation.
Okay, 10 is right. 6, I don't know.
Okay.
6, I don't know, but actually the next one will have a 10 in it, the next power. Maybe let's just do one more and we'll see if we can't see the pattern then. Let's do one more. And then we'll take a stab at the final guess. Okay. So I'm going to take my matrix here. That's the matrix I'm taking the power of. And oops, let's bring this down for later. And we'll take this matrix here. And this is going to be the calculation for n equaling 4. Okay. So again, we have an upper triangular matrix, which gives me 6 of the entries already. Now I just have to compute these other 3 entries. So I'll take the first row and the second column. I get 3 plus 1 plus 0. That's 4. Now I'm going to take the first row and the last column. I get 6 plus 3 plus 1. That is 10. And now I'll take the second row, third column, and I will get 3 plus 1 again, or 0 plus 3 plus 1, which is 4. So now let's take a look here. Let me move my 1 over so I can see it as a pattern. Let's look at this entry. What do we get? For n equaling 1, we get 1. For n equaling 2, we get 2. For n equaling 3, we get 3. For n equaling 4, we get 4. Now, I think my daughter could figure that out. not to be, you know, everyone can figure that one out. So we're going to guess. Right? Let's guess with a pattern here. We're going to guess that these higher, well, we have that we're always going to get this upper triangular matrix with ones on the diagonal, at least from what I've said. And now we're going to guess that this first row, second entry is going to be n. Similarly, if we look at the second row, third entry, we get 1, 2, 3, 4. So that I'm also going to guess to be n. Now the tricky one. This entry, we get 1, we get 3, we get 6, we get 10. Do you recognize these numbers?
I'm working it out. So I think it has to do with previous n.
I'm going to draw a little
Okay.
picture,
Okay.
if you don't mind. These numbers have a name, actually. If I make a triangle and I count, say of height n, and I count the number of dots in it. So here's a triangle of height 1, say 2, 3. I will get that these numbers are following that pattern. These are called triangle numbers, or triangular numbers. I don't remember, one of the two. They're kind of big in, well, they're very useful actually for a lot of reasons, but there is a formula for them, and it's the binomial coefficient. So these numbers I can look at n, I'm sorry, let's say n plus 1. So if I look at these numbers, the formula for these numbers will be n plus 1, choose 2. Have you seen this before? This is called a binomial coefficient. If you ever do any statistics, you will need to learn quite a bit about these numbers. They're ever present whenever you're doing any probability theory or statistics. Not just the n plus 1 choose 2. It's this n plus or n choose k in general. Let me write it a little more clearly. This number it's written n plus 1 choose 2, but so that's notation. But let me give you the expression that computes it. So this is equal to, well, so the formula for there are two formulas. I mean, there's a general n choose k formula, which is easy to write down, but for this particular one, this is going to be n plus 1 times n over 2. That's what this is. So let's check and see if that's right here for these numbers. So for n equaling 1, this number will be 1 times 2 over 2. That's 1. Matches. For n equaling 2, the number is going to be 2 times 3 over 2, which is 3. N equaling 3, I get 3 times 4 over 2, that's 3 times 2, that's 6. And here you can check for 4, I get 4 over 2, say 2 times 5, that's 10. So indeed, this is a number you will have seen before. So if you don't know this, if you don't know binomial coefficients, okay, let me just say a couple of words really quickly about them. In general, there's a formula for n choose k. It's n factorial over k factorial times n minus k factorial. These numbers appear in something that you probably have seen before called Pascal's triangle. You can build Pascal's triangle like thus, and you'll start seeing these numbers appear. In fact, if you look along the second sort of diagonal row, right here, you'll notice that pattern. 1, 3, 6, 10. This is the one we've got here. All of these binomial coefficients actually sit in this triangle, this Pascal triangle. Really beautiful, beautiful subject. So we're going to guess in our formula that this number this upper right-hand corner is going to be n times n plus 1 over 2. So that, to me, is the fun part. The fun part is coming up with what this actually might be. And now, maybe the less fun part is proving it, but it's not hard. So while it may not be as fun, it's not difficult. So we just have to follow the prescription for proof by induction.
That is excellent.
So, and there is something mathematically important about what we're doing here. We were just being scientists right there, right? We were doing an experiment. We ran the experiment by doing a bunch of computations. We looked at the data from our experiment and we came up with a hypothesis that we could come up with a pattern, and we wrote down a formula. Now that's a scientific method, and it's a great thing to be able to do as a mathematician. It's very important. But now we want to be mathematicians and sit and verify this, not through experiment, but rather through proof. Okay. And so we're going to do that. And with proof by induction, there are two steps. The first step is to prove your statement when your parameter, the parameter you're going to induct on is 1, or is its smallest value. So all proofs by induction are proofs about some formula or some statement involving a natural number or a positive integer or some discrete step-by-step parameter. In this case, it's on n. We're inducting on n. So here we have to take what's called the base case, which is n equaling 1. We'll say n equaling 1. You might be able to do n equaling 0, but let's do n equaling 1. This isn't hard. So we need to verify our formula for n equaling 1. Okay. Well, let me just take this. This is n equaling 1. That's just the matrix, right? But I'm going to write it in a really silly way. Well, I don't know how I can write it in a silly way here. I just have to write it down. But now I'm going to write it in a very silly way here. I'm just putting 1 into my formula. Okay, well, this is definitely true. Okay. I'm just verifying that indeed this does satisfy the formula. Of course, this to the 1 is itself, so it does satisfy the formula. So the base case is no problem. There are some proofs by induction where the base case is kind of the hardest part. This is not one of them. The next step is called the induction step. And this usually is where you have to do the work. It's not much work here, but it's work. So what do you do in the induction step? We assume the formula is true for n. And we want to prove it's true for n plus 1, pardon me. And what's the idea behind mathematical induction? The idea here is the following. I like to view it as a ladder, okay? The base case is like the lowest rung of the ladder. Let's say I have a ladder going up infinitely high. I want to know that I can get as high as I want on that ladder. What do I need to know? I need to know first that I can get on the lowest rung of the ladder. If I can't do that, like if it's too far above me or something, right? And I can't climb the ladder. So the base case is all about saying, okay, you can get on the ladder. The induction step is saying, literally, you can go from one rung to the next rung. If you can do those two things, you can get as high as you want, just by repeating second step over and over again until you get high enough. Then it's true. Then it's true that you can get as high as you want. This is what mathematical induction is saying. It's saying if it's true for the first case, and if you can go up a case, then you can get, then it's going to be true for all of the cases. All right, so let's assume this formula is true for n and we want to get to the next step. So what we're going to do, I've got to look at that formula, because I'm going to write down the formula or the left-hand side for n plus 1, what I want to prove. But I can't actually, you don't just write down the left-hand side then, you've got to actually do something. But what you have to do in this case is just compute. So here I have, this is the left-hand side of the formula for n plus 1. And now, again, do not just write down the right-hand side for n plus 1. Rather, let's take a look at what we're doing here. If we're taking an n plus first power, that's the same thing as taking this matrix, make it big enough, and then multiplying, let's have a little more room, sorry. Multiplying it by this to the nth power. Right? Put a little times to make sure that it's. But now you use what's known as the induction hypothesis. The induction hypothesis, I mean, we're trying to prove an induction step. We're not trying to start at the beginning and get all the way to n plus 1. We're assuming this thing is true for n. Well, here we have it for n. So we can use the formula for n.
Okay.
So I'll write that here. Oops, incorrectly. Here I'm just going to use my n formula. Now I just have to do matrix multiplication. Well, let's see. So again, these are both upward triangular matrices, even though I've got n's in them and so on, and they have ones along the diagonal. So I can quickly enter 6 of the entries. Now I have to do some multiplication. So I'm going to take the first row in the second column and multiply. So I get 1 times n plus 1 times 1 plus 1 times 0. So that's n plus 1. Life is looking good so far. If I take the second row and the third column, then I get 0 times this mess, which is 0, plus 1 times n plus 1 times 1, which is n plus 1 yet again. Now I have to deal with the last and kind of the sort of more messy case. So the first row in the last column. So for that, I'm going to give myself sufficient room here, maybe get a little bigger here. I need to take 1 times 1, I'm sorry, pardon me, 1 times n plus 1 over 2. So that is, I'm going to write this one out, n times n plus 1 over 2, plus 1 times n, which is n, plus 1 times 1, which is 1. All right, so let me take a look at that on the side here. And just write, and it's helpful to write down what you're doing. So now this is equal to n times n plus 1, I'll just rewrite it, over 2 plus 2 times n plus 1 over 2, right? Just multiplying n and 1 by 2, which is going to equal, now I can factor out the factor of n plus 1. It's going to be n plus 2 times n plus 1 over 2. Just pulling out that factor of n plus 1. And I'll just commute. I'll rewrite this as n plus 1 times n plus 2. And in fact, I'll do even better. I'll commute and I'll write it in a really stupid way. N plus 1 plus 1. Right, n plus 2 is n plus 1 plus 1. And why do I want to write that? Well, because what I want to do is say, thus, when I look back at my the thing that I'm looking at, this original n plus first power, and I replace this expression, which is written here, with what I found here, I will get that this is equal to this guy. Let me do it. Duplicate it, bring it down. But now I'm going to do that replacement. And now what do I see? Well, what I see is when I look back up the formula that I wanted to prove, and I replace n, all these n's, with n plus 1, including this n, with n plus 1, I have precisely this equation. So what I was able to do in this long kind of calculation is say, okay, if it's true for n, which I used right here, then just through some basic calculation, I see that it's true for n plus 1. That is the induction step. And here you're done. That's the end of the proof. You can always write, thus it's been shown, or and we're done, or whatever you want to write.
I think satisfying with that.
Yeah, sometimes people like QED or whatever. It's your choice. So there it is. Thank you, Matt, for forcing me to make this video. I hope it helped.
Thank you so much.